The tan graph is an entirely different animal compared to the cos and the sine graphs, which are really similar to each other. The tan graph's really special. And the way that you're going to remember the shape of the tan graph is that it is a water slide in between two poles. Now you'll remember from the hyperbola graph and the exponential graph that there are these things called asymptotes, and these guys are asymptotes. Okay, so I put a table down. The first time you draw a tan graph, you should work from a table, but thereafter you can just recognize the pattern and draw it from there. When you do this on the calculator, this one's a lot longer than the sine and the cos graphs, and it's because you need to go up in 45s. Okay, because some of these are going to blank out, some of them are going to go math error, and I'll tell you which ones they are now. This one's going to be a math error, which means it's an asymptote. Okay, this one will be a math error, it's going to be an asymptote, and also this one, and also this one. So between negative 360 and positive 360, there's going to be 4 asymptotes. So when you plug this into the calculator, you're going to get math error on each one of those. Okay, for the rest, I'll fill in those numbers now. So what it has in common with the sine and the cos graphs is that it still really only goes between 0, 1, -1, and then there's all these asymptotes everywhere. So when you have asymptotes in a graph, like the exponential and hyperbola, draw them in first, because it helps you with boundaries. It helps you to understand where else you're allowed to draw, because clearly on the asymptotes you're not allowed to draw anything. So I'm going to fill in at all the asymptotes. I'm going to fill in my dotted lines here, and then I know that I can't draw anything that crosses the asymptote, because the asymptote is the don't touch me. It's the line through which nothing else may go. Okay, so I've given you the picture already. It's going to be a water slide between two poles. You can see it's going to do that. This one's not symmetrical about the y-axis because it's actually going to go through it. Okay, now we're going to plot some points, and then I'm going to show you how to connect them. So on negative 360, it's a 0. And I'm just going to plot all the zeros so you can see where it goes here. Negative 180 is a 0. On 0, it's a 0. Then on 180 it's a 0, and on 360 it's a 0. Just want you to see the pattern. Okay, so you can see that it's going to be there. So I'm going to have something that goes like that, it's going to cross over, and there's going to be some little tails at the bottom and the top of the water slides at the top. Now let me plot in my 1s and -1s. So on negative 315, which is between negative 270 and negative 360, it's that little one there, then that's going to be 1. So you can see the shape is going to go there. It's actually not going to finish. It's not going to be a complete water slide. Okay, then if I go further on negative 225, which is in between 180 and 270, it's -1. So you can see it's going to go like that. Okay, and I'm going to fill in the rest now. Right, so what you can see is a series of what looks like diagonal lines. Now, just to make a point, I want to show you what happens if you enter in a number that gets you more or less 2. Okay, so if I take on my calculator tan of 63 degrees, I get 1,96, which is really close to 2. I just want to show you, if I plot that, how it helps me understand the shape of the tan graph. Okay, I've got to approximate here. If that's 45, which is in between 0 and 90, then more or less a third of the way is going to be about 60. Okay, so if that gives me about 2, look at that. It certainly isn't going to help me with my diagonal lines. You can see what happens here is that shape curves, and it's going to do exactly the same in each one of these water slides that's in between the two poles. So the way we're going to join them is bearing in mind that asymptotic. So you can see this one is only covering 90 degrees. It would need another 90 to get its other shape in, and we're not going to finish it. So what happens to each of these sets of 3 is they do what all graphs do by asymptotes. They try to get really close to the asymptote, but they never get there. So that's how to remind yourself what an asymptote is. So this graph looks completely different to the sine and the cos graph. And you need to remember to curve so that you get the right shape. There's also something really different about this graph. One shape is one water slide between the two poles. So you get an entire tan graph in that amount of space and another entire one there. This one's easy to see. How many degrees are there between 90 and 270? It's 180, right? So that means that the tan's graph has a period of 180 degrees because it only takes 180 degrees to finish an entire shape. And that's also what makes it really different to the sine and the cos graphs, who have a period each of 360 degrees. The other thing is that while we can see that that is technically a 1 for the a value, and we can look at the formula y equals a tan x plus q, this, while it's technically the amplitude, you can see that this graph doesn't have an amplitude. It doesn't have how far up and how far down it goes. So there's no amplitude in a tan graph. This does tell us about the stretch though. So like other graphs, the a value is about the vertical stretch factor. And we'll see that now when we do some changes. So right now, the fact that that's a 1 in there tells us how far it goes when it hits 45 degrees. And then you can see if this was perhaps higher and it was a 2, the whole graph would be quite a bit thinner. But we'll look at that in a moment. These graphs then go off to infinity, so we do need to put some arrows on in each direction. And from now on, you don't need to draw the entire table. Once you've got the concept, then just remember water slide between two poles and make sure that it's on your 45s and those repetitions in between, that you then have your 1 or whatever that value is over there. Then you can understand, you won't even need to put that one in, you can just see it's going to approach the asymptote in each case. You'll just need to label that point and the intercepts with the axes, and all the other points that are in the same position as you go along. A reminder that the way to approach drawing the tan graph is to make sure that you're going up in 45s, even if you don't label it, because we can see that if that's 90 and that's 0, that one has to be 45. And the other thing is, for now, until we start shifting things left and right, which we only do in grade 11, you can just put in the asymptotes immediately. They're always going to be at the 90s and 270s. So your whole setup for the tan graph needs to be there before you even start drawing things in. Okay, so for the normal tan graph, the original one, tan 45 is 1, tan of negative 45 is negative 1, tan of 0 is 0, and that's pretty much your shape. So I'm going to draw the middle one first, and then I'm putting my arrows on because I know it goes off to infinity, and that's that. Okay. Then for the other ones, it's going to mirror exactly the same shape. It's going to be one of these there, and then there'll be a tail and a head on each of the sides. A good rule of thumb is to remember that you're going to end up with this set of 3 dots that slopes to the right, and then you're just going to connect them. So what happens if we make changes to the a value? In the formula it's the amplitude, but as I explained a moment ago, there isn't an amplitude for the tan graph. So what happens when we change there? Okay, so if this number gets bigger, then your graph just becomes a lot thinner, or steeper. Okay, so that's one way to look at it. And then if this one becomes smaller, then it starts flattening out a little bit. It becomes a lot flatter. So you need those mental models in your head so that you understand if this is bigger than 1, you're going to end up with something a lot steeper. And if it is smaller than 1, you're going to end up with something that's quite flat. Let's try the graph of y equals 2 tan x. Now you can plug this into your calculator and you'll see that all that happens is the zeros stay the same, just like the cos and the sine graph, but where you normally had tan 45 as 1, you now have 2 tan 45, so it's obviously 2 times 1. So what happens is that all the 1's become 2, and all the negative 1's become negative 2. When I plot in my points that are now going to be the graph of 2 tan x, I'm just circling the zeros because they stay the same, and then you can see that these have jumped up 1. So again, the whole thing has stretched between the top and the bottom. Now when I draw in my graph, and I'm going to do the middle one first, you can see that yes, it's going to approach the asymptote, but it's going to do that quite a bit slower, because here this curve does that. I'm just going to let it extend a bit beyond the brown graph so you can get a sense of what's happening, that the whole thing is a lot steeper, it's a lot closer to the y-axis, very much like the parabola and the exponential function. With the graph of y equals a half tan x, every time there would have been tan 45 giving you 1, it's now going to be a half of tan 45. It's going to be it's a half of 1. So where this used to be at 45 and 1, it's now going to be at 45 and a half. So all the 1's now become a half, and all the negative 1's become negative a half. So you can see this thing's going to flatten out quite a bit, and we'll be able to see the 3 together when I join all the dots. Right, joining them here, I'm going to start with the middle one again. It's going to get to the asymptotes quite a bit quicker. So you can see it still goes through 0, right? But you can see that it's getting to the asymptote quite a bit quicker. So I'm just going to draw it slightly shorter than the brown graph so you get a sense of it, because they all approach the asymptotes anyway. So this one just is a lot flatter. It's got this sort of shape, whereas the normal graph does that water slide, and then one with a really high A value is a much steeper one. So you can picture that kind of water slide is going to be a lot more difficult, whereas that would be like one for children. So I don't know if that helps, but it may get the mental models in your head that the smaller A value would be for smaller children. Maybe that would help. So those are the 3 together, and all that's happened is the amplitude is shifted. So what do you think is going to happen if we now shift the Q value up or down? Think about it before you see it. Remember that no matter what type of tan graph you're drawing, you need to prepare the space. So your Cartesian plane looks a little bit different. Mark out your 90, 180, 270, 360. Do that. And mark out the little centimeters in between. I will always use a scale of 2 centimeters for a tan graph so that you can have your 45s in between. Otherwise it gets a little bit technical when trying to draw those curves, especially if they've been shifted. So what if we want tan x plus 1? There's my original graph, which I would draw in pencil, and then all that's happening is that the entire graph is shifting up by 1. So that means that every single one of these critical points, and there's 3 of them in the tan shape, is going to go up by 1. So I'm going to start with the middle one and then expand on either side. This one was 1, so it's now going to be 45 and 2. Okay, and this one was 0, 0, so it's now going to be 0 and 1. So my little set of 3 is going to go like that. It's going up by 1 there. So I now have 3, but it's the exact graph excepting a whole lot higher. Okay, so I'll just show you how that looks there, and then we'll fill in the rest. So it's sort of like the shape, it looks like the shape that's been moved up by 1, and it must look like that, but it's really difficult to get the perfect shape, so don't stress too much about that. Okay, moving every other point up, we end up with our little sets of 3 like that, and now connecting them, we've got the same idea. So the whole graph has been shifted up by 1. Let's now shift it down by 2. If we shift the whole graph down by 2, each of the brown points, the critical points, are going to be shifted down by 2. So starting with the middle one, that will be down there, and then I'm going to have again my little set of 3 dots, but it's going to be there, there, and there. So this one moves down by 2, this one's moved down by 2, and that one's moved down by 2. And then I can just copy and paste that pattern along the bottom here. Drawing it in is going to have the same idea, but just remember that this is kind of your middle point now. So it'll go a lot higher than lower because we've actually shifted it down, but the Cartesian plane has stayed the same. So just remember that you have a water slide shape when you draw it in. And if you're going from negative 360 to 360, you're going to have the tail on that side and then the head on the other side. So you can see what's happened in each case, that was on 0, it's now negative 2, so that has moved down 2, 1, 2 jumps. From the brown one it goes down 2, brown one goes down 2. So if that just helps you understand. So my light blue graph is the graph of y equals tan x, but shifted down by 2 units. So what about negative tan x, when everything gets reflected in the x-axis? How would that look? So all the positive ones will now become negative and the zeros stay the same. So now I've got that down there and this will stay the same. Okay, so it'll be going down. Think about it like that. Okay, so what's essentially going to happen is you did have a graph that was going like that and sort of increasing, if that makes sense. And now what we're going to have is a water slide that's going down from left to right. So this one will go up here. That one stays the same, this one goes down there. So here, you've got a graph that does that. So all that happens when it goes negative is you end up making like little x's if you keep the original graph there as well. So this time my 3 dots go from left to right instead of going up in the other direction. But the principle of reflecting makes sense. It's exactly this, but down there. And the brown one went like that, and so its reflection is there, if that makes sense there. Okay, so you can see that the whole thing has been reflected in the x-axis. What if we've got multiple transformations? So first of all, it's negative, so it's reflected. Then the amplitude is 2, so the whole thing's going to be skinnier. And then we are shifting the whole thing down by 1. So first we're going to do that. We're going to make it negative. So we've already got that. We've got the green one. Then we will change the green one to have a higher amplitude, and then we'll shift the whole thing down by 1, as follows. I'm now changing the green graph, which is already negative, and I'm making its amplitude bigger. So all of my 1s become 2, and the zeros stay the same. So you can see I'm going to have a thinner graph again. I'll draw the middle one first. Okay, so it sort of comes in the inside of it here. And of course it's still my backwards graph. Okay, then from the light blue I'm going to shift the whole thing down by 1. So shift every one of these little blue dots down by 1 to get the final dark blue graph. So if you look at the new dot pattern, but start with the middle one, you can see I've still got those 3. They're just further apart because my amplitude has changed. So I've basically got the light blue graph and the whole thing has shifted down. So it'll look like that.